Okay, mic check, mic check. I'm just testing this again. Okay, mic check, mic check. I'm just testing this again. Cool. All right, we're back at it. So I finished working out a problem earlier, and now I want to work on a problem that I want to do. And so that's going to be working on Rabi oscillations. Cool. I actually never really understood them, and I had done an experiment on it in an experimental course, and it kind of sucks that I didn't know what was going on. And today I attended a presentation by Professor Roberto Merlin at the University of Michigan, and I learned a lot. It was pretty cool. Um, and so some of the things that we went over was basically the basic setup of a system, of a two-level system, and the description of the Hamiltonian. And he left a lot of stuff for us to work out, and I just thought it'd be neat for us to work it out. It's going to be connected into a whole nother problem set with flowcat states, but we're only going to do this. So for now, we just have a two-level system. And so we have two levels in our quantum mechanical system. We have our ground state, which we'll denote using the Brocket notation, is with G for the ground state, and an excited state, which we'll denote E with the Brocket notation. And so basically we could occupy either the ground state or the excited state. And in this system, we will have an oscillating potential. So you could just think of, well, what would have an oscillating potential? Whenever you have a light wave, we usually draw it out like this, and you have the kind of magnetic component oscillating back and forth perpendicular. So you have your E field going up, down, and your B field perpendicular to it, right? With your light wave source traveling in what this looks like, it's going to be an E field, and it's dependent on the frequency and the time or position. Um, and so it's going to look something like this. The real component of it, of course. And so our Hamiltonian, which describes all the dynamics for this, is written as basically the ground state. So EG, and then the projection of the ground state plus EE, which is the energy of the excited state. We have the projection of the excited state, and then we have plus basically this interaction term. So he actually wrote it FO. He describes it like this, with this coupling term. And so it's EG because it's like, what are the chances basically of getting excited from going from E to G and then later on from G to E. And then we have the off diagonal terms written like this. And then the complex conjugate, I'll write it out. He just wrote CC, but we have this F star VGE, because it's a complex conjugate, I omega T, and then we have G, E. All right. And that's it. That's for the Rabi oscillations. And we're going to kind of start trying to work out some of the things that he mentioned. And so for this problem, we want to work out the Schrodinger equation, which will look something like this. The time dependent one. So this is where we're stepping up into putting on our big boy pants. And we make an assumption with h bar is equal to 1. It's just to make it a little neater. And so this right here is the Schrodinger equation. Man, I hope I spelled it right. Okay, and with the Schrodinger equation, um, it's a differential equation, and so you know how we learned in Diffie Q classes, it's basically you guess the solution, and we come up with the solution that I guess it makes sense in this and it's very general, and so our solution, it's a function of time. We're gonna make a guess, and our guess is it's exponential. So e to the I g eg times time, and then we have a constant. So we're going to consider a ground state, and then we have g plus e to the I e, so it's the energy of the excited state. Then we have a constant. Boom. Okay, and so let's take a step back. Let's just look at our Hamiltonian, right? The only states that we're really considering, even if we just look at this, is just the two states. We either have, you know, our um, a particle in the energy state of G, and it could get excited to E, or it could come down from E to G, right? And so it makes sense that if we have a wave function, it's gonna either have a waveform of it being in G, the ground state, or of it being in E. And so we said this is a general state, right? This is dependent on time. This could actually be just the conjugate of this times any constant. So this is very general, right? But the key part about this is trying to find out what this constant is. And so that's what we're gonna do. We're gonna want to plug this into here and see what we get out, right? Okay. And before we just plug it straight in, let's just maybe spend a little more time with this Hamiltonian, right? So I mentioned this is a projection. This is a projection because if you have any type of wave function, say right here, and you were just to plug in this g out, you would basically get this g component out, right? And so I'll probably do a whole video on that in itself, Dirac notation. I might have actually done one, but I could go more in depth and we can play around with it and the linear algebra of it, because I think it's pretty important. But yeah, this Hamiltonian, you basically have the ground state energy coming out, this excited state energy coming out, and this is a coupling term. So if you were to only have a ground state term, you'd get this term out, right? The excited state, it would be what hopping over to this, and in the other end as well, from the excited state to the ground state. And so we just have these four terms, and now we're basically going to apply this h to this Hamiltonian, or to this wave function, and then take the derivative with respect to time of this wave function as well. So let's plug this h to here. And so we get h times this wave function is equal to, okay, we're going to get this eg out. And so let's take a moment to see how I'm doing this, right? So if I was to apply this projection, let's go aside real quick right here. If I apply g to g, this inner product is equal to 1. Because we're making an assumption that in these two states, we have a Hilbert space and that it's orthonormal, such that when you apply this to itself in these basis states, it's equal to 1. So for both, for the excited state and the ground state. And when you have it equal in the opposite, this is equal to 0. Because these are considered orthogonal to one another, the excited state and the ground state. And so if I was to apply this H here, this G component would complete this one right here. So you'd end up getting this G1. And you're left with the G right here. So you get this stuff with this G and a G. So you get E, G with this exponential T out. And when you apply this to this, you get 0. So we don't consider that term. So now let's go to the next term. This E part. Oop, we're not done. You get this coming out, and you get G. So that's just getting this first term to applying it to this whole thing. This term is 0. You only get something from here. You get this out. So that's why this is a projector. You only get the G part out. And so now when you get to this part, it's the same thing. It's another projector for this E part out. So you apply this to this side. Remember, you get this E to the G. And remember, E or G to E to G, applied to G gets you 0. So we don't consider this term with this term. It only applies to this E term. And so you're left with E, E little e, and then the exponential with this constant, and you get the same E term back because when you apply this E to this, you get 1, and you're left with this. Okay, and then so now we apply this term to this. And one thing to consider is you see this G gets applied to this G, but you're left with an E. So you'll actually end up getting FOV EG E to the I omega T. Oh, and we would have gotten this whole, then now this whole bit in E to the negative I E G T times C G T, and we get this. Ooh, no. This G erases this G, and to become 1, and you're left with E. So this should be E. And then we do the same thing. Oh, then you apply this one to this E, but remember, G to the E, they're orthogonal, you get 0. So you don't count that term. And so now with this final term, we do the same thing. We get FO conjugate VGE E to the I omega T times, so this E goes to this E. This one gets canceled through orthogonal. So 0, so we don't even consider that term. So you're left with the G. Um, and so we are applying it to here. And we get left with, so this E cancels this E for 1, and you get G. Okay, so all this algebra is just to basically get this side. And so now we have to do this side, which might seem a little more complicated. But it's not going to be too bad. Okay, and so now when we look at this, we have I times the time derivative of all of this, which is interesting. And remember to note that there is a time derivative, that we have to apply the time derivative here and here. So we have 2 terms, which means we have to do a product rule in calculus. So we take the derivative with respect to t of this first term. We get e to the, we get I e minus I e g out times the whole term, and it doesn't change that. And then we still have the gt, and then we take the time derivative with respect to this, and we get this times the time derivative, which we'll denote with the little dot above. This denotes time derivative times the g states. And notice how this g state doesn't vary with time, so we leave it as such, or else we'd have to do the product rule to these three terms, getting 6 terms out. Fortunately, we put this one term, we just have to do it there. And so then we do the time derivative for this term, and there's 2 terms. And so we'll take the time derivative of this first, getting minus I e out, e to the minus I e t c e t, and this has this term, and then plus, and so then we take the time derivative with respect to this, so then we still get this term, and again we take the time derivative and we denote it by putting a dot above. Okay, and so that's this term here. And so maybe what we should have done on this side, and we still could, but we should maybe group up the terms just to make it look a little nicer. Um, so this, we'll keep the I out here just for now. And what we can factor this thing out, get minus I to the EG, this out, plus this, and then we get plus, we can factor out these terms, this is a lot of algebra, but this is good practice nonetheless. Because we got to learn how to take into account um, our mathematics. Okay, we could do the same with this top term, but we're gonna kind of see what direction we have to take this. So let me refer to the notes real quick. So in this case, we end up just kind of getting an answer. Okay. So let's see what we get. So one thing that's interesting to note is the G's are gonna have to match, and the E's are gonna have to match. So we have our G terms and our E terms, right? And so if we look at our Hamiltonian up here, we see that some terms are gonna have to match. And so let's group up our G terms right here as well. So I'll rewrite this down here. but grouping up the g's like we did here. So we group this term up. And then we group this term up. Oop, never mind. Not this term. This is the one with the G. This bottom one's the one with the G. So we have this. This is GE n times that. Plus, and then let's now group up our excited state terms. So that was the first term, and then this term. Okay, and so now the one thing to note. So remember this term is denoted for here. Remember that these two are equal to each other, right? For the Schrodinger equation. And so for things to match, in order for these two things to be equal, this term right here, I'll maybe denote it in this color. This term right here, because it's the G term, has to match this term for this G term. And then this term for the E term has to match this one for this E term. And so it's going to lead to some more fun calculations. And so let's set them equal to each other, right? We're going to get this, write it out here to the side. First, we're going to work on this term. Just a little colon to denote that we're working on this G term. Okay, so we got EG to the EIG, ET, I guess before, instead of just, I'll continue writing it all out. Yeah, I'm just kind of tempted to be a little lazy and not show the steps, but I think it might be important so others could see. And I guess in me working it out more, I'll I'll be more involved. It'll stay better in my head. Yeah, and so note. Oops. I accidentally wrote down. Oh yeah, no. I did want to write this bottom part. So this bottom part is equal to this top part, right? And so right here, when we distribute this I times I is equal to negative 1. Negative 1 times negative is positive. And so this thing right here is equal to positive EG e to the negative I g e g t c g plus e to the negative I e g t c g. Okay, I just want to double check something real quick because I only see a time derivative here, but not here. And I suspect I might have messed something up. Okay. Yes, right here. There should have been a time derivative here from this term. Okay, let's make sure we got that correct here. Yep, when we're writing this term, we have our time derivative here. Okay. And so before moving on, one thing to recognize is these two terms right here are the same. So we can minus them both from both sides, leaving us with an equation for the g side, right? And we get this. We're left with the conjugate for FO VGE EI omega t e to the negative I EE, I believe. Let me double check. Yep, EE. And this is equal to e to the negative IG t and the time derivative component of this. Neat. Okay. Let me see. Ooh, we are missing one thing. So I applied this I term here, but I forgot to apply it here. So let's see where that would go. It would go right here. That means there would be an I right here. Okay, and so let's further simplify this by moving this exponential to the other side. And we can do that by multiplying both sides by e to the plus I EGT. And that's going to give us, if we move this to the other side, if we flip the order, we're going to have CG, the time derivative of CG, times I is equal to FO VG GE, my apologies. And then we can start factoring out a lot of these parts. So this positive term should be here. And so if we were to factor out a minus I, this term is positive. Since this was positive, because we put it on this side now, we factored out a minus, it goes minus. EG, and this is positive, so it would go minus as well. Times that. So now we actually have an equation. What we'll notice is that this is going to be a coupled equation because a CG, the time derivative of CG is going to depend on CE. But now what we need to do is solve for this for the E terms. So we'll save this equation here for now and solve for the E terms. And so for this, we have this whole mess right here. keep wanting to write Q. This is an omega. And this whole thing is equal to this. And remember, there's this I is distributing here. So this I to this I is going to be minus. To the minus, it's going to be positive. So we'll get an E, E, and what do you know? These two terms are the same. Again, what do you think we're going to do? We're going to cancel them out before they could even make a second appearance on the page. And so this I, let's not forget it to distribute here, but to distribute here as we write out that term as well. And so when we write this term, I guess I'll do it how I did it on the other one. I'll write down both terms. This is equal to this side. And so again, like the other problem, we're going to want to solve for this, moving this to the other side. And so we get I times the time derivative of a constant. And so when we move this to the other side, we're going to want to do the similar thing. And so this is going to be positive now. And so we're going to have FOVEG. So this time we're going to want to have e to the I instead of minus I. We see that we get positive EE minus EG minus omega t times CG of t. And what do we know? We have two coupled equations where this one is dependent on this and this one is dependent on this. So that's pretty neat. And one way to solve for this, okay, for those who might not know or be as familiar, is you could take the time derivative with respect to this again, and we'll see what we get. So if I was to take the time derivative of this with respect to t, we're actually going to get this is CG. Oh, hold up. Let me think about this real quick. How does this work? Yeah, there's a few different ways we can do it. We can take the time derivative of this with respect to t, but then we're still going to get that term out. What we can also do is move this over to the other side, and then just plug this into the other side, which still basically takes the time derivative of it. Oh, yeah, that'll be fine. That'll be fine. Okay, so take the time let's just, yeah, we'll take the time derivative of this and then plug this into there. So we'll take this, take the time derivative of it. And then now we take the time derivative of this. And notice how we have two terms that depend on t again. And so I guess before we move forward, I'd probably like to simplify some terms. And I'd like to basically make this theta is equal to EE minus EG minus omega. It's just so that way this term will just be e to the minus omega t. It's just instead of writing out the whole entire thing, I'll make it a lot easier. And so when we're taking the time derivative of this, when we take the time derivative of this part, we're going to take down in a minus I omega times f. Oh, let's factor out the constants real quick. F G E, because we're taking it of this. Time derivative of this minus I theta times this plus the same term, but now we got to take the time derivative of this. Okay. Then now let's see where we stand with this. Did we make any progress? Okay. Yeah, I'm sorry. It's because I'm working this out myself for the first time as well. Hmm. Yeah, if anyone else was here, I'd probably ask for assistance from the chat. I don't really have a friend right here that would help me calculate this, or else I would phone a friend as well. But let's try to work it out. Let's just keep at it. Okay. We have this term. We have this term. Oh, okay, this is a neato part. Watch. This right here, the CE, if we move this stuff to the other side, it's equal to C dot G. So what we want to do is basically just solve for all one. We want CGs. Instead, we don't want a mix of CGs and CEs. So this term, I can plug in this equation into here. And we'll have CG here, no problem. But this term, I was a little confused about. I wasn't sure what to do. But we do have a term of CE right here. Right here. So this one I'll write down real quick. We have CE as a function of t is equal to I CG dot divided by FO VGE, and then we have, because we're moving this to the other side, this becomes a plus now. I omega t. And so now we have something that we could plug in. Oh, yeah, CG right here. And so let's plug that into here and see what we get. e to the I theta t. When you plug this bad boy into here, ooh, neato. So we're actually gonna have these cancel out, because from here, and then we get a times, or we get divided by this, and we get CG times I out, but with a dot. And so remember, this is this term right here, plus, and we look continue on, I theta t, and this term, we're gonna put this term in. So we'd have to divide this I over to the other side. We have FOVEG times e to the I theta t, remember this is theta, g of t, and we can't forget to divide by I. And so let's now see what we're at with this. We'll rewrite this and we'll distribute this out. So this term cancels out with these two. These cancel out. I times I is minus 1 times minus is positive. So we're literally just left with CG. Oh, times theta. Can't forget the theta. Times theta. And then when we plug this stuff into here, well, we actually have, so notice that these two terms are complex conjugates of each other. So they're actually going to end up being the absolute value of these terms. Oh, my apologies. So these aren't within the exponential. This is its own thing. This is times. And so these cancel out with each other. This I on the bottom and CG. Okay, and this is what we get. And so from our differential equations course, remember all of these are dependent on time. There is a way to solve this. And the way to solve for this is basically through a method of exponentials, where you solve this almost as a quadratic equation. And the answer to that, if I was to just throw it to y'all, which I don't know if it's satisfactory. If somebody complains, I'll probably do something about that. But basically, we get that CG ends up equaling some type of constant that's dependent on G. No, it's not dependent on G. It's just a constant, and we get um, exponential solutions out, and we get two terms out. Because remember, in a quadratic equation, there's two things you get out, and so this is going to be equal to minus theta over 2 plus or minus radical theta squared plus 4 times this inside part out. Then all this is over 2 as well. And so this is definitely like the quadratic equation. Just for simplicity, this part right here, this is for the future. reference. This is going to be equal to capital omega, I believe. Is that a capital omega or is that capital? Yep, capital omega. And notice how this looks definitely has a form very similar to the quadratic equation. If you were to assume this is like the squared term, like x squared, you have the a, b, and c term. This is where all this comes from, or how it plays into it. Yeah, and so this is pretty neat to see. And you'll have an analogous one um, for the exponential term. And so just so that way I could keep moving along, let's maybe revisit what we've done so far. So remember, in this system, because we don't want to just get bogged down in this, we got to remember we're doing this for a reason. We're solving a two level system, and we have basically oscillating terms. And so one thing that's interesting is within a wave um, form, apparently this is called the rotating wave approximation. I'm gonna have to investigate this a little further because normally when you just think of an oscillating field, it should be a cosine or sine term. We'll use complex exponentials, and I don't remember the exact way to solve it, but you can't solve this apparently an exact solution if you don't use this rotating wave approximation. Okay, and we wrote our Hamiltonian. We have the ground state, the excited state, and then we have the transition states. And we wrote down the Schrodinger equation. We made an ansatz of what we think this solution is, and then we wanted to solve for what these constants were. We plugged this in to the Schrodinger equation. So we plugged in the Hamiltonian for each term. Then we took the time derivative for this other side, times it by I. We made h bar equal to 1. We remember that our basis sets are orthonormal, and which means that if you multiply one of the bases by itself, you take the inner product, you get 1. If you take the inner product of two different bases, you get 0, meaning they're orthogonal. And then when you solve for one side and the other side, you want to then match the ground state coefficients, and the excited state coefficients with the excited state. You separate it out and you work it out. You see that these two cancel out. Remember, you're going to do product rule when you take time derivative. And as you start working it out, you see that they're coupled. The equations are coupled right here and right here with the stars. And so what you want to do is solve for one of these. So then we could repeat the process for CE as well. We just did it for CG, where basically we took the time derivative of both sides here. Boom, we did it to this one. And when you do it to this side, there's two terms that are dependent on time. So you're gonna get two separate terms because of a product rule again. This lone CE term, we plugged this same equation back in to get us a single time derivative of CG with one time derivative, and this other term we basically plug in our other equation because it has a CG term. And now that we got this equation, we can solve it using differential equation tactics, giving us this solution. And so notice how we actually do have a decaying term. I just noticed that. Oh, no, we don't actually. This is still all real valued. I guess it might depend on these values. We didn't go too in depth into the working out what this stuff means. So hopefully I'll be able to do that soon after, because this is just part 1 of 3 lectures, and I'll try to work it out soon after the other ones. And so if I was to then look at continuing it on, they had rewritten the solution. And so I'll just write down the solution. But I've been able to work this out, so it makes sense to me. We have exponential. We have the plus or minus capital omega times another exponential I theta to the t over 2. And so remember, this omega is, we solved it right here, this value. And then we have this part out. This is divided by the square root of 4. And then we have this term. And so this is just a constant in front of everything. And then here are the individual terms for the ground state. And for the, this for the ground state. And for the excited state. And so the actual solution for this is going to depend on the initial boundary conditions. This is a 2. Let me make it a little crisper. And so, yeah, the solution, it's made up of the solution is made up of the positive term. Because notice how we have a plus minus and the minus part. And so if we were to I'm just writing out a little bit more. If we were to start off with the assumption that we began in the ground state. So if this is equal to the ground state. So say we begin in the ground state at time equals 0. And then we basically turned on an alternating E field. This is the equation that we'd get as a function of time. So this is the ground state term. And then for the excited term, like this is pretty interesting to see. So if time equals 0, this is 0, this is 0. So sine of something 0 is equal to 0. So this is 0. This term would be 0 as well. This is 0. But one thing that's really interesting to see is that even though our field is oscillating with respect to small omega, right? If we go back up here, how do we write our Hamiltonian? We have e to the I omega t. Our field is switching and moving with respect to this omega. But how are we transitioning from the ground state and an excited state? Well, what we notice is that it doesn't depend on this omega. It's actually capital omega, which we found is equal to this whole thing. And so it's just fascinating to see that. And one of the things that was made sure to really point out is that these Rabi oscillations, it's not based on linear response, because the linear response theory says that if you were to basically apply something at like an omega, it would oscillate with that same omega, but instead we have capital omega, which isn't um, linearly based on this. And so that was kind of like the big reveal of it for today's part of the lecture. But I think there's going to be more to come, because this is the initial setup. I think the final setup later on is, which is a little more complicated, is that we have our two-level system, our ground state and our excited state. But now we're going to couple this to a continuum of states. And I think he called it chi e. And so we're going to add a few more terms. And so this is still a two-level system coupled to that. So one thing he mentioned in the very beginning of the lecture is that when you just have a single state coupled to a continuum, this is called the Friedrich. I'm not sure how to say it. It's Frederick's problem, and this has been solved for a long while. And what we just solved is like the Rabi problem. And so, yeah, there's more to come, and I look forward to seeing the presentation to see how these terms decay and how it just all works together. I'm not as familiar with this quantum optics type deal, but I know it's important for materials, especially with certain excitations. And so hopefully we could tie it into some other stuff we learn, and we can maybe wrap it up in a way that and present this in a way that people could better understand it. Okay, but I think that might be all for today. Overall, there's a few other things I'd like to share that I've learned today. I might just share it tomorrow. But in the meantime, stay curious, and let's keep working on our math and the rest of our problems. All right, y'all take care. Bye bye.